Good morning, my dear students. Welcome back to my chemistry class. Today I am going to discuss about the new chapter, that is Ionic Equilibria. Ionic Equilibria. Okay, so to consider various equilibria involving ions of strong weak acid and weak bases. So the chapter we have to discuss the equilibria involving weak acid and weak bases. Okay, we have to discuss the equilibria involving weak acid and weak bases and compare the relative strength of the acid Ka with respect to Ka and relative strength of the base with respect to Kb. The dissociation constant of acid and dissociation constant of bases. Okay, and we are actually employing basically that is based on the Oswald dilution law. So in order to account this relative strength of acid and bases, or to have to discuss the equilibria involving strong acid and weak acid and weak bases, we have to derive the Oswald dilution law. So all this is explained on the basis of Oswald dilution law. Okay, this is very important. The next, we have to pass on to the pH of a solution. Then pOH, then pKa, pKb and pKw. All this concept or the pH, along with the pH, we have to define the parameters pOH, pKa, pKb and pKw and significance. Then after that we have to go through what is a buffer solution. Buffer solution, its classification and Henderson equation. Of buffer solution is very important. Henderson equation for a typical buffer, so as said, but basic buffer. This derivation is very important, Henderson equation. And then the mechanism or the buffer action of buffer mechanism of that is the mechanism of buffer action of a buffer. So it is how it resists the change in pH. So you have to explain. So these are important things: the buffer solution and its classification and Henderson equation for buffer solution mechanism or the buffer action of a buffer solution. The next is important is the salt and hydrolysis salt. Different types of salt. Salt, classification, then hydrolysis of salts, various types of salts, and the nature of their aqueous solution. The nature, explanation of the nature of the aqueous solution. So what is salt hydrolysis? You have to go through that. Salt hydrolysis and define the hydrolysis constant K, that is salt K. Yes, Ks. Hydrolysis constant you have to define, and you have to explain the nature of the aqueous solution of the salt based on the hydrolysis. After that, you have to derive the expression for Ks, the hydrolysis constant Ks, with respect to Ka, Kb and Kw. This is also very important. So to derive the expression for the hydrolysis constant of various salts. Okay, we have different types of salts. So we have to derive the expression for Ks of different types of salt and their relation with respect to the Kw or K or Kb through Kw. We have to derive. This is very important. So these are the important the things we have to discuss in the topic Ionic Equilibria. So before passing into details into this chapter, I wish to give you some of the elementary idea of acid, bases and salt. So we can, after discussion of the preliminary theories of acid and bases, we can pass on to this Ionic Equilibria. So, theories of acid and bases. Various theories of acid and bases. Okay. We can discuss the various theory one by one. The first theory, that is the classical theory, that is the Arrhenius theory. Arrhenius theory is the most simple theory. This is the first theory that is suggested for an acid and a base. That is, according to this, an acid is any substance that can liberate proton when dissolved in water, while base is any substance that can liberate or generate OH minus or hydroxyl ion when dissolved in water. That's all. So this is a theory that is stipulated for aqueous system or in water. So it is, that is according to this concept, Arrhenius concept, an acid is a proton donor in water, while base is an hydroxyl ion donor. Okay. But the important, the limitation is theory is that it is a selective theory. We cannot explain the basic character of certain substances which does not contain hydroxyl ion. Similarly, we cannot explain certain basic character, acidic character of certain substance which does not involve H plus ion. So it is actually, that is a hydroxylic protic concept, or it is typically explained in water only, so it has some limitation. So there is so Arrhenius theory, which says that an acid is a substance that can liberate or generate proton in water, dissolved in water, while base is any substance that can liberate hydroxyl ion when dissolved in water. And it is a selective theory. But the second theory, that is somewhat more generalized theory, that is Lowry-Bronsted theory. Lowry-Bronsted theory, that is the most generalized theory. It is a generalized theory. This theory says that this is actually a proton concept. This is actually a proton concept theory. It's a proton concept. But based on the proton, we can explain. But the Lowry-Bronsted concept, actually is a proton concept. It says that an acid is any substance which can that is generate proton, gives a proton to any other substance, while base is any substance that can accept proton from any other substance. So this is a theory in which acid and base action go hand in hand or simultaneously. So a substance to behaves as an acid by donating proton, there should be another substance should be present that can accept the proton, thus acting as a base. Thus, according to this theory, an acid and base, it is always act like a pair or acid-base pair. It is always go hand in hand. That is a peculiarity to the theory. So any theory or any substance that can generate a proton, gives off a proton, generate a proton, there should be another substance that would be present that can accept the proton, or that should be act as a base. So this is a theory in which an acid and a base always takes place in pair. A base pair takes place in the reaction. Okay? That is, if a substance acting as an acid by generating a proton or gives a proton, the other part, usually a solvent, acts as a base and thus accept the proton. While if a base can accept a proton from any other substance, the other part, the solvent, the other species the solvent should behave as an acid so as to liberate a proton. So always it will go hand in hand. That is a very important theory. It's easy to understand. So, Lowry-Bronsted concept, that is a proton concept. An acid is any substance that gives a proton to any other substance, while base is a substance that can accept proton from any other substance. So, always that acid and base reaction go hand in hand. Okay. And two, it involves, it brings the concept of conjugate base, a pair. conjugate pair. It introduces a concept called a conjugate pair. So, Lorentz concept introduces a concept called conjugate pair. What is a conjugate pair? When an acid gives up a proton to act as an acid, when a particular substance gives off a proton to act as an acid to the base, the remaining part, the anion can take back or accept or can accept or take back the proton, or you can take the proton back and therefore act as an acid base. That's the situation. You know that when an acid like HA when react with the base H2O, so that by donating proton, the remaining part, you know that the remaining part A minus, that is we have H3O plus A minus, the remaining part anion. This anion can, so when an acid gives a proton to the base to act as an acid, the residual part is an anion. This anion can accept the proton back. This anion can accept the proton back. Okay, proton back, and thus it acts as a base. So this is called the conjugated base of an acid, H. Okay, this is called acid 1 and this is base 1. So they are called conjugate pair. Conjugate pair. What is a conjugate pair? That is the things. A pair of an acid and a base. Again, I wish to say, the Lorentz concept introduced a concept called the conjugate pair. In any acid-base reaction, there are two pair of conjugate pair. There are two set of conjugate pair in any acid-base reaction. A conjugate pair is that pair of acid and a base which differ by a single proton and are formed one from the other. That's the thing. A conjugate pair is a pair of acid and a base which differ by a single proton and are formed one from the other. They are called acid 1, base 1. Similarly, there are acid 2 and base 2. Therefore, any acid-base reaction thus involves two conjugate pair or contain two conjugate pair. One is acid 1, base 1 and the other is acid 2, base 2. This is acid 2. This is, as we have already used it, acid 1 and this is its base, this conjugate base is base 1. Then this is H2O plus can donate or gives off a proton that acting as an acid, this is acid 2 and therefore this is a base 2. This is another conjugate pair. Conjugate pair. So, a pair of acid and a base which differed by a single proton and are formed one off from the other is called a conjugate pair. Any acid-base reaction thus encounter two set of conjugate pair called acid 1, base 1, one pair, and other is acid 2, base 2. Then the relative strength of the acids and base. This theory says that the strength of an acid and a base depends on the easiness by which it can donate or gives a proton or it can accept a proton. The strength of an acid depends on the easiness by which it can release protons. Similarly, the strength of the base depends on the easiness by which it can accept proton. So, if an acid can liberate its proton very quickly, okay, to a large extent or very quickly, it can act as a strong acid. On the other hand, a substance can act as a base can act as a strong base if it can accept its proton very quickly. Okay, very quickly, or it is easy to accept the proton in a large quantity very quickly. How it depends? You look here. It depends on the stability of its conjugate base. So, more stronger the acid, when you look at more stable its conjugated base. That's the thing. If the conjugated base of an acid, one is a most stable, or is a weak base, is a weak base, then the acid is a strong acid. Your HA acid 1 is stronger. If A minus 1 is more stable, you consider the case. And let's try. You consider the case of that is HCl plus H2 gives H3O plus Cl minus. In this case, you know, look here, the chloride ion, this is acid 1 and this is base 1. The conjugated base of hydrochloric acid, that is Cl minus, ion is more stable than HCl. Therefore, chloride ion is a weaker base. It's a weaker base. Therefore, HCl is a strong acid. Here on the other hand, you look here, H2 and H3. H2 and H3. Here acid 2. And this is base 2. Base 2. Here considerably, you look here, consider this, comparing this, you consider this, these are in the species, here hydrochloric acid is an acid. We want to compare the strength of the hydrochloric acid in terms of its stability of the conjugated, that's all. The acid HCl is a strong acid as its conjugated base is more stable. Cl minus is more stable and has a less tendency to accept the proton back to convert HCl. So always the equilibrium shift towards right. Therefore, the equilibrium shift more towards right. Okay. Equilibrium shift more towards right. So it is a strong acid. On the other hand, you consider other acid, that is CH3COH, all of you know. CH3COOH plus H2 reversibly gives, look at this equation, look at in this reaction, or in this case, we have the CH3CO minus, okay, we have the hydronium ion, H3O plus CH3CO minus. Here, the anion, acetic acid on losing, give a proton to H2 to give an anion. This is the conjugate base, H3COH, base 1, acid 1. We look here, what is the case? Acid 2, base 2. Conjugate pair, this is conjugate pair. You look at what is the strength of acetic acid. Here, the acetic acid is considered as a weak acid because its conjugated base CH3CO minus is less stable than acetic acid. That's the situation. The conjugated base of acetic acid, that is CH3CO minus, acetate ion, is less stable than acetic acid, hence it has the tendency to accept a proton, and easily converted to CH3COH. So the equilibrium shift towards left. Here, look here, the equilibrium, that is purposefully I am written in this manner. This is left. So the equilibrium shift more towards left. Because acetate ion is a stronger base than, comparatively stronger base than water. And it has a tendency to accept a proton and convert to acetic acid. What you have to say is acetate ion is less stable than acetic acid, hence it can accept proton back easily and equilibrium shift towards left. So acetic acid is a weak acid. The next, another thing is that, case of water. If water is the solvent, the liberated H plus ion combines with the solvent water molecule and exists as a more stable hydronium ion. H plus H2 combines to gives the more stable hydronium ion. So H plus ion in water combines as exists as hydronium ion, the most stable species. And another interesting thing is that according to Lowry-Bronsted concept, the water solvent molecule is such that it can act both as an acid and as a base, so it is considered as an amphiprotic solvent. So another concept is that in the Lowry-Bronsted concept, water is a amphiprotic that can act as both as an acid and a base. When it reacts with an acid like HCl, you look at HCl, water can act as a base because it can accept proton. It can accept proton and thus act as a base. Okay, the equilibrium is more shift to its light. And you have hydronium ion plus Cl minus. So it acts as a base. But when it reacts with the NS3, look at NS3. When NS3, water combines with the NS3, what is actually happening is that it can donate proton. Water can donate proton to NS3 and thus it acts as an acid. As an acid. It gives, that is NH4 plus OH minus. NH4 plus OH minus. This situation. So in this case, water acts as an acid by donating the proton. In this case, water acts as a base by accepting a proton. Therefore, water is considered as an amphiprotic solvent. Bicarbonate is also an amphiprotic species. Okay, all these are examples. Typically, we are a solvent. Water is a solvent, is considered as an amphiprotic solvent. That is a peculiarity of Lowry-Bronsted concept, and it is a more generalized concept. We can explain the various basic characteristics of acid and bases using this theory here. You have to know that both acid and base have a dual character. If a substance acting as an acid, the other substance is a solvent as well as a base. Similarly, a substance acts as a base, the other species acting as a solvent as well as an acid. That's the peculiarity. Okay. And you have to explain the stability of an acid or base in terms of its conjugate part. More stable the conjugate part of an species, okay, more stable than stronger that species, stronger that acid or base. In the next case, the other theory comes. That is the Lewis concept, Lewis theory. This is an electron pair concept. Electron pair concept. Or electron concept. What is this theory? An acid is any substance that can accept a pair of electrons from any other substance, while base is any substance that can donate a pair of electrons to any other substance. Therefore, according to this electron pair concept, an acid and base reaction takes place between an electron deficient compound with any electron rich compound. That's the thing. Any electron deficient compound that can accept a pair of electrons can act as an acid, such as called a Lewis acid. Similarly, any substance which contain excess pair of electron, non-bonding electron in it, that species acting as a base, that is called Lewis base. Example of Lewis base are NS3, contain lone pair. Even H2O can also act as a Lewis base. Okay. So any anion that contain lone pair of electron act as a Lewis base. Similarly, this is an example of Lewis base. F minus, okay, etc. O2 minus. All these are Lewis bases. Cl minus even can act as a Lewis bases. Similarly, any electron deficit compound or any compound that contain that is vacant d electron in it, like heavy metal compound. Heavy metal compound contain unpaired d electron in it. stannous chloride of SbF5, etc., they can extend their electron units beyond the octet. They are also acting as considered as electron deficient compound. Similarly, H plus is an electron deficient. BF3 in boron, in BF3 is electron deficient. Aluminium trichloride, aluminium is boron, that is electron deficient. So we can say H plus, then boron in BF3, AlCl3, FeCl3, etc. Then SbF5, SbCl3, SbCl5, etc. All SnCl4. All these compounds such that they are considered as electron deficient. Here these compounds can extend their electron beyond the octet by accepting the electron in their vacant d orbital. Okay, in the vacant d orbital from the Lewis acid. So all these compounds can act as a Lewis acid. Lewis acid. So any compound that contain electron deficient atom like H plus, BF3, AlCl3, FeCl3, etc. acting as a Lewis acid. Similarly, any compound that can contain unpaired d electron in it, so vacant d electron in it, like SbF5, SbCl5, etc. Stannous chloride, they can extend their electron number beyond the octet. Okay, in the vacant d orbital can consider as a Lewis acid. So this is an example. So generally, the complex formation, any cation, electron cation can be considered as a electron Lewis acid. Okay, Ag plus, because it can accept electron pair from a Lewis base. So that we can account the formation of the complex between the ligand and heavy metal can be a Lewis base. It considers an acid-base reaction. So according to Lewis theory, consider an acid is an electron pair acceptor, while base is an electron pair donor. Thus, we can very well explain the formation of NH4. NH3 can combine. NH3 with this lone pair can donate its electron to the electron deficient H plus, like this. So donation. So we have the compound NH4 plus. Okay, the compound NH4 plus thus is produced. Similarly, you have the piece of L3 Br, that is BF3 BF3 LCl3 BF3 complex, that is NS3 BF3 complex. You had a formation of NS3 BF3 complex, NS3 AlCl3 complex. All these are possible because the ammonia can donate its lone pair of electron to electron deficient boron, thus produce the NS3 BF3 complex like this. NS3 BF3 complex. Okay, this is produced like this. And we can account the formation of the complex Ag combines with the Cl minus or F minus in water. Okay, all this is an example of Lewis concept. F minus plus BF3 giving BF4 minus, Ag plus 2Cn giving AgCN2, etc. Ag plus 2Cn giving AgCN2, NS3 BF3, SiF4 plus 2F minus. SiF4 plus F2F minus giving SiF6 2 minus. This is a complicated compound that is produced. This is acting as a Lewis acid. This is acting as Lewis base. Okay, that's the theory. So I hope that we have explained most of the theory. There are two other theory I just mentioned, that is Lax flood concept. Lax flood theory. Lax flood. Symbol for that is, according to these concepts, an acid is a substance that can donate an oxide ion or anion to any other substance, while base is a substance that can accept. That is, a base is a substance that can donate oxide ion or anion to any other substance, while an acid is any substance that can accept oxide ion or negative anion from any other substance. So it's an oxide concept or anion concept. And so acid is an oxide O2 minus acceptor. O2 minus acceptor, while base is an O2 minus donor. So here the calcium oxide plus CO2 giving, here they have CaCO3. The result is a salt. So it's a neutralization process. And anyway, any acid-base reaction results in the formation of the salt. The common species is salt. So here calcium oxide, then acidic, that is an oxide, that is metallic oxide, donate oxide ion, okay, transfer oxide ion to carbon dioxide, which is an acidic oxide, which is a metallic oxide, is a non-metallic oxide. We have a salt calcium oxide. So the reaction between a metallic oxide and a non-metallic oxide can be considered as an acid-base reaction according to Lexfoot concept. According to the metallic oxide acting as a base, while non-metallic oxide acting as an acid. Interestingly, a metallic oxide dissolves in water, you have the base. Similarly, interestingly, the non-metallic acid oxide we dissolve in water, we have the acid. Carbonic acid, carbon dioxide. CaO giving calcium hydroxide. SO2 giving sulfurous acid. Okay. Similarly, aluminum oxide giving aluminum trioxide. Interesting, that is the sodium oxide gives sodium hydroxide. So any other metallic or non-metallic oxide dissolves in water gives the acid. Any metallic oxide dissolves in water gives the base. But here consider even the terms of oxide. According to Lexfoot concept, a base is an oxide ion donor, while an acid is an oxide ion acceptor. You always go hand in hand. The last is the Ionic concept. This is the most general theory. Actually, it is a combination of various theories. That is Ionic concept. Ionic concept is considered as a universal theory. According to this concept, and any substance that can produce or give up cation, any substance that can produce or give up cation or take up anion or electron or react with a base to form salt is considered an acid. So that is, we are incorporating all of the other theories here. So any substance that can gives gives or produces a cation or give up cation. Any substance that can produce or give up cation or that can take up anion or that can accept electron or that can react with a base is called as an acid. Similarly, a base is a substance that can give up anion, that can give up or generate anion or accept proton. Generate anion or accept proton, or that can gives electron. Remember, a base is any substance that can generate anion, or gives up anion or electron, or takes up cation or react with an acid. That is directly opposite to that is acid. An acid is a substance that can generate or produce cation, or that can take anion or take electron. Okay. Or react with a base is called an acid. Similarly, a base is any substance that can give off or generate anion or takes cation or that can liberate electron. Okay. So a substance that can gives off anion or electron or that can accept a cation or react with an acid is form a base. That's all. The next, we have to explain the concept of your leveling solvent. And differentiating solvent. This is something very important. So based on the Lowry-Brons's theory, you know that an acid can exhibit this strength, and similarly base also can exhibit this strength in aqueous or in solvent. Though the relative strength of an acid or a base depends on the nature of the solvent in which it dissolves. That's the situation. So the base, if an acid acting as an acid, to act as an acid, the other part, that is the solvent, acts to be acting as a base. So depending on the nature of the solvent or base, acid can, that is said to be, behaves in a leveled, completely dissolved or ionized, or to acting as strong acid, or it may be partially ionized. Similarly the case, if a substance acting as a base, the other part, the solvent should, the nature of the solvent depend, determine the strength of the acid and the base. So that is the behavior of the, so the nature of the solvent is very important in determining the strength shown by an acid or a base. The relative strength shown by an acid and a base in a solvent depends on the characteristic of the solvent. It depends on the ability of the solvent to leveling off the ionization, leveling off the species, or its ability to differentiating the species. And means depends on the ability of the solvent to produce ionization. It depends on the ability of the solvent to produce ionization fully or partially. So what is a leveling solvent? What is a leveling solvent? That is, if an acid is dissolved in a solvent such that if an acid ionizes completely, fully in the solvent, so that all the acid behave equally strong, such a solvent is said to be leveling solvent, because the solvent can level off the ionization of the solvent completely. The solvent can level off the ionization of the acid in that solvent medium. Therefore, that solvent is said to be an leveling solvent, so that all the acid behave equally strong. That is a definition. So, then what is a solvent whose proton accepting character tendency is such that the different acids ionize to same extent and appear equally strong is said to be a leveling solvent, and this phenomena is called a leveling off of the solvents. Okay, that is, if a solvent can accept, the solvent has a tendency to accept acid from proton from different acids, okay, to the same extent that they are equally ionized. They are all equal, different acids get equally ionized to the same level, equally ionized to the same level. Then such a solvent is said to be a leveling solvent, and the whole acid behave equally strong in such a solvent. For example, all the acid like H2SO4, HCl, HNO3, etc. Okay, HCl4, etc. When dissolves in water, all these acids when dissolves in the water, they level off to the same extent. Water post ionization completed to the same level, H3O plus Cl minus. Here, H2SO4 plus H2O giving. Okay. H3O plus SO4 2 minus. Then balanced equation H3O plus. Okay. Then next is HNO3 plus H2O giving H3O plus NO3 minus. Here water is said to be in leveled off the acids. The ionization of the salt, all the acids are equally, all the acids are equally ionized to the extent of the leveling of the hydronium ion. You know that here the hydronium ion all the acids are ionized to the equally to the level of the hydronium ion here. All the acids HCl, H2SO4 and HNO3. HCl, H2SO4, HNO3, they are equally ionized by H2O to the completely and to the same level as that of the level of the hydronium ion. Therefore, all the acid behaves equally strongly in water. So, water is said to be a leveling solvent, and this phenomenon is called a leveling off. In this case, you are here. All the acids are ionized to the level of the hydronium ion. So the most stable species, the hydronium ion is the most stable species. So, hydronium ion is more stable than HCl. Similarly, chloride ion is more stable than HCl. So, all the acids here are leveled or ionized to the same level as that of the hydronium ion. So, they are behaving equally strong in water. So, all are strong acid in water. But that is not the case. Acetic acid. Now, acetic acid when dissolved in water, they have the reaction like this: CH3, CO minus plus that is H3O plus. In this case, this acetic acid is not completely ionized to the level of hydronium ion as like this. So it is a weak acid. Similarly, the various weak acid. You look here, C6H5COH plus H2O giving CH3, C6H5, CO minus plus H3O plus. So all the weak acid. Okay, what I want to say is that what is leveling of solvent or what is a leveling solvent? A solvent that you can accept or that you can donate proton such that the different acid are ionized to the same level in that solvent, and they are all equally ionized to the level of the hydronium ion in that solvent. Then the solvent is said to be a leveling solvent, and all the different acids are equally strong in such a solvent. But what is a differentiating solvent? Example I have mentioned. All HCl, H2SO4, HNO3 are ionized to the same extent to the level of hydronium ion. They are equally strong in water. What is a differentiating solvent? Okay. A solvent that can ionize the acid to different extent, to different level in that solvent such that their ionizing strength is different or they are measured, then such a solvent is called a differentiating solvent. A solvent whose proton accepting tendency is such that different acid ionizes to different extent and their relative strength can vary in the solvent and they can be measured, is called a differentiating solvent. That is the case. In the case of acetic acid, benzoic acid, formic acid, all this organic acid, when dissolves in the water, they are ionized to different extent and their relative strength can be measured, or they are different. They are not leveled. Such a solvent, water is said to be a differentiating solvent in this case. But the same water is a leveling solid in the case HCl H2SO4. The case of ammonia also, you know that. In the case of ammonia, when dissolved in water, ammonia, amine, NH2 minus, C6, RNH2. They are considered as weak bases because they are differentiating. They are, they are ionized to a different extent. In the water. Therefore, they are said to be RNH3 plus OH minus. Hence, they are said to be differentiating solvents. So, an acid such as solvent which has a tendency to ionizes the different acid to different extent so that the relative strength can be easily measured and vary, and they can be measured. Such a solvent is said to be a differentiating solvent. But you know, depending on the nature of the solvent, we can vary the nature of the acid. You know, the HCl, HNO3, they can act as a strong base, strong acid in water. So water is a differentiating solvent. But the same acids, when dissolved in, that is, dissolved in another acid, like what we should say, yes, that is HF, I think. HF, you know that? Yes. HNO3, HF. You look here. When acetic acid, consider the case. Acetic acid, when dissolved in ammonia. When acetic acid dissolves in ammonia, the ammonia acting as a leveling base. But acetic acid acting as a weak base because water acting as a differentiating solvent. So ammonia acting as a leveling solvent for acetic acid. But you look here, water acting as a leveling solvent for acetic acid. But the acetic acid, when dissolves in ammonia acting as an what I said, water acting as a leveling solvent for acetic acid. But when what is replaced as ammonia, when ammonia is acting as a solvent, acetic acid acting as a leveling solvent. That I wish to say. Acetic acid is fully ionized, just like HCl. Instead of H2O, if you are taking ammonia. That is the thing. The presence of ammonia, acetic acid acting as a strong acid, so ammonia is a leveling solvent. That's the situation. What I wish to say is that HCl, H2SO4, HNO3 acting as a differentiating solvent, acid, that is that they have relative different, they have relative strength, they have and it's a different extent if HF is using as a solvent. If you are using HF as the solvent, this HF acting as a differentiating solvent for HCl, H2SO4, HNO3, etc. That's what you have to remember. That is the situation. That is, you are contrasting that thing, don't confuse. Acetic acid plus H2O giving CH3CO minus plus H3O plus. Here it is an differentiating solvent. Because ionization is not complete and it vary with a different acids. But the acetic acids, when dissolved in NH3 giving CH3CO minus plus NH4 plus. Here it is a leveling solvent. Ammonia acting as a leveling solvent. Okay, ammonia acting as a leveling solvent, but water acting as a differentiating solvent for acid with respect to acetic acid. Similarly, HCl, HNO3, etc. I have explained with the water. Okay, acting as a leveling solvent, but they, when react with HCl, when react with HF, okay, it reacts like this. H2 plus Cl plus F minus. Similarly it gives H2 plus NO3 plus F minus. In this case, it is acting as a differentiating solvent. Differentiating solvent. Here, HF acting as a differentiating solvent for HCl and HNO3. So, definition again, a solvent which can level off the ionization of the acid or proton into that the level of H3O plus, so that all the acid get ionizes equally in that solvent, that is said to be a leveling of solvent. So the all the acid behave equally strong. That is the case of HCl, HNO3, sulfuric acid with respiratory water. On the other hand, if a solvent that can ionizes the acid to different extent so that the relative strength can be measured or vary, such an solvent is said to be a differentiating solvent. That's it. Okay. Time being, I am going to wind up the class. Thank you very much.